My name is Ashley Palmer, and I'm the Conservation Education Specialist at the Northern Virginia Soil and Water Conservation District. And I am the Envirothon Coordinator for Fairfax County, and assuming you're here at our local training, you are also one of the teams or one of the coaches or one of the students participating in the Fairfax County Envirothon this year. So if you have any questions about how our local competition is going to look this year or anything like that, you can please feel free to direct those my way. And then we also have some amazing presenters here today to talk to us a little bit about soils and forestry. And our soils expert has volunteered to talk to us a little bit first. Dan Schwartz here has a bachelor's and a master's degree in environmental science from the University of Maryland and Virginia Tech respectively, and is a Virginia licensed soil scientist. Since 2003, Dan has worked for the Northern Virginia Soil and Water Conservation District in Fairfax, Virginia. He helps to update the county soil survey, assists homeowners with erosion and drainage problems, conducts research on urban soils and stormwater control, and has been an Envirothon judge and presenter for 16 years. So both of our presenters today have a wealth of knowledge and experience that they can talk to you about. They also have the benefit of being the people who are writing our local tests. So hint, hint, anything they're presenting on, they may think is important. So with that, let me go ahead and turn it over to Dan, and he'll give us our presentation on soils. I am moderating the chat box, so should you have questions at any time during the presentation, please feel free to put them in there. And if they're relevant to a particular slide Dan's on, we'll let him know. And then otherwise, we'll ask him some more of those questions there at the end. So from here, I'll turn it over to you, Dan. You can go ahead and share your screen.
All right, so let's get started. So, starting off, I wanted to go over some basic concepts of what soil is. And some of you may have seen my presentations before, and I kind of always start with this slide. This is not so much of a scientific concept, it's more of a conceptual idea. Something to wrap your head around, a way to think about soil that may be a little different than the way most people do. And I think it's probably more of an accurate way. So we can say that soil is the skin of the earth. We can also say that it is the intersection of the three spheres of matter. What are these three spheres? Well, there's the hydrosphere. That's all of our water from basically the oceans down to the largest rivers, down to the smallest streams, down to the little tiny droplets of water you'll find in the soil moisture as well as up in the clouds. All that combined together. Ice caps as well too. That liquid or solid water is the hydrosphere. The lithosphere is all of our rock. So no matter where you are in the world, if you dig down deep enough, you will eventually hit bedrock. And of course, as bedrock breaks down, those little particles of rock that weather from it are also part of the lithosphere. And then lastly, there's the atmosphere, which is the air above us. Where all three of those things mixed together right there at the skin of the earth, right at the surface, that's where we get soil. So it's important to think of soil as a mix of water, air, and rock. Generally, we think of soil as being a solid material, which is not wrong, but water and air are very important and very large constituents of soil that we need to take into account. So if we were to look at a healthy soil, emphasis on healthy, because not everybody has healthy soil around here, but let's say we do. If we have a healthy soil, it would be about 50% solid, 25% by volume air, and 25% by volume water. That means a full half of the soil is taken up by either air or water, and only half of the soil is solid, which is generally quite a bit less than we might think. Of those solids, we could break it down and say 45% of the soil is mineral matter or mineral solids, 5% is organic solids. Get into what those are in a little bit. So even though the solids are only 50% of the soil, they're very important 50% of the soil, because oftentimes when we're describing the characteristics of soil or the differences in soil from one spot to another, we're really making comments on the soil solids. How do they change from one location to the next? So soil solids, even though only 50% of the soil, maybe less than we originally thought they were, they still are extremely important. So let's look at those fractions that I talked about, the mineral fraction and the organic fraction. The mineral fraction, 45% of the volume of the soil, is very simply just sand, silt, and clay within the soil. What is sand, silt, and clay? Those are the different types of particles that weather from that solid bedrock. The difference between sand, silt, and clay is purely a matter of size. Sand is a larger particle, silt is a smaller particle, and clay is the smallest. There's different ways to look at this depending on which organization or government agency you're talking to, they might define sand and silt and clay a little bit differently, but generally we use the U.S. Department of Agriculture's definition. And they say that sand is any mineral between 2 and 0.05 millimeters in diameter. You don't really have to memorize these numbers by any means. These are just to show you the differences in sizes. Silt is any mineral between 0.05 and 0.002 millimeters, and clay is any mineral with a particle diameter less than 0.002 millimeters. So with this interesting breakdown, sand, silt, and clay just being broken down by size, you could have a particle of, let's say, granite bedrock that you break down, and you can have that same exact particle mineral formation, the exact same atomic structure, same minerals inside, and it could be a particle of sand, a particle of silt, or a particle of clay, strictly based upon its size, its width, or diameter. So when we're looking at clay, the smallest particle there, what does 0.002 millimeters really mean? That's the same as 2 microns, 2 millionths of a meter. So clay is really small. Anything less than 2 millionths of a meter, a mineral would be a particle of clay. Silt is also very small. Both clay and silt are entirely microscopic. And sand is a little bit macroscopic, a little bit microscopic. Towards the larger end, 2 millimeters, you can certainly see that with just your naked eye. As we start getting down to 0.05 millimeters, that's when we start getting into the microscopic range. But the important thing to remember here is sand and silt and clay, although they seem very small to us, have very different particle sizes. Sand is a lot bigger than silt, and silt is a lot bigger than clay. And when we're talking about the composition of the soil, one important term you'll hear frequently is something called the soil's texture, and that is just the percentage of sand, silt, and clay within your soil. So sand, silt, and clay not only creates the feel of the soil, it creates what we call the soil's texture, which has a lot of effect on the soil's behavior. That's 45% of the volume of the soil right there. The other 5% of the soil solids is your organic fraction. And that consists of living material in the soil. So these beetles, earthworms, the living roots themselves, we consider those to be parts of the soil. And then the smaller stuff, like the smaller invertebrates, smaller insects, and then the very small microscopic bacteria in the middle, and then soil fungi over here are all part of the living portion of the organic fraction of the soil. Now, even though these small guys are invisible to us, especially the bacteria and the fungi, they're extremely important and extremely numerous. It's estimated for every teaspoon of topsoil, there's anywhere from about 100 million to 1 billion bacteria living within that teaspoon of topsoil. For the fungi, it's a little hard to count exact numbers because they're multicellular. But if we were able to take all these little microscopic fungi, we call them roots or root hairs or hyphae. Basically, they're like little white pieces of twine, fungal twine that work their way through the soil. If we were to take all these microscopic fungi roots and lay them end to end to end, per teaspoon, we'd have anywhere from about 40 yards to 40 miles of roots. So there's really a tremendous amount of material, living material in the soil. Most of it is invisible to us, though, because it's microscopic. Then we have the dead organic portion. And this would be most noticeably here, the leaf fall that comes down during the autumn, but any other dead organic material that drops onto the soil surface, whether it's a dead animal, whether it's twigs or branches, even just the blades of grass that you cut while you're mowing your lawn and you leave it on the soil surface, or animal manures. All that stuff is dead organic material that gets deposited and incorporated into the soil as well. Oftentimes it's incorporated by the living organic material. They see that dead material and they see that as their food source. So what is soil really then? If it's got all this living material in it, is it the intersection of the hydrosphere, the lithosphere, and the atmosphere? Is it this mix of sand, silt, and clay and organics? It is, but perhaps we're sort of whistling past the primary function of soil. It's a very, very rich soil, very, very rich food web and ecosystem. There's a tremendous amount of stuff living in the soil, but because it's invisible to us, it's underground, and so much of it is microscopic, we don't see it, and sometimes we sort of forget about all this energy and carbon that's cycling around in the soil food web just below our feet. Certainly we see the above ground food web, the plants we eat, the animals we eat, other animals that eat other animals and such, but we don't really see the below ground food web as much, but soil has a tremendously rich, varied, and important food web, and therefore is also a very tremendously rich and varied ecosystem too. And at the base of that food web is that soil organic matter, the dead soil organic matter, residues from plants, the leaf fall, the dead stuff that falls on the soil surface. And there's one other very important source of soil organic matter, and that's actually the plant roots themselves. Oddly enough, plant roots exude or push out a lot of organic matter into the below ground portion of the soil. And there's theory is they do this actually to sort of kickstart the soil food web, because the soil food web, as organic matter is broken down through the soil food web, it releases nutrients that the plants can use. So it's in the plant's interest to have a very highly functioning and diverse soil food web. So let's recap. Soil is the skin of the earth, conceptually. It's 50% solid materials, 25% by volume air, 25% by volume water. Those solids are composed of mineral material, both sand, silt, and clay, and those three particles are separated by their diameter, or their particle size, and organic fractions. And it's also a very complex ecosystem and a very complex food web. And it needs one final thing for it to be considered soil. It has to be able to support plant life. You've got all those things up above, skin of the earth, 50% solid, 25% air, 25% water, so on and so forth. You still need to be able to grow plants on it. Crops, wild plants, anything. So while some people say that the moon and Mars have soil on it, from a soil science perspective, we actually would say that that's not soil because it's not able to support plant life. So how do we get this soil? How do we get these little particles of sand, silt, and clay, and these this rich ecosystem and food web, and this decomposing organic matter and living organic matter? How does this come to be? Well, it's of course a very natural process, but also a fairly slow process. So we could say that soil is a renewable natural resource, but it's not really renewable on the human time scale. So to give you an example, how long does it take to break down bedrock? Let's say you've got a big chunk of granite bedrock just sitting up at the surface. If you go to Yosemite National Park, you'll see great chunks of granite bedrock. Famous cliffs there are made out of granite. And they've probably been there for thousands, millions, who knows how many years. Well, obviously it's going to take a long time to break down that solid chunk of granite and turn it into those little particles of sand, silt, and clay. So we could say, hundreds, thousands, probably more like thousands to millions of years to really start breaking down that bedrock. Breaking down organics, that's a faster process. If you throw some organic material for some kitchen scraps into your compost pile and come back the next day, you'll see that they're beginning to visibly break down. They're darkening, they're beginning to look a little rotten. But there's a lot of more resistant organics out there as well too. Specifically, I'm thinking of soil humus. As material breaks down, as the material in your compost pile breaks down, it creates soil humus. And that soil humus is so useful for gardeners, for farmers, for anybody interested in growing stuff, because it stays in the soil for a long time. Humus can take 50, 100, 150 years to fully break down. So for organics, we can say it's a matter of days, hours in some cases for some of the easiest to break down stuff, up to centuries to really see that organic decomposition process run its full gamut. So we kind of combine these two together. We find that in a very general average, it takes anywhere from about 100 to 500 years to create every inch of soil. And if we look at the soils around us, oops. Oh, shoot, I got my animation wrong. Well, anyway, our soils around us anywhere could be, on average, I'd say about 3.5 to 4 feet or so thick. Sometimes they're thicker, sometimes they're a little bit thinner. Let's say we have our average soil pictured here. Sorry about the bad visuals. So 3.5 feet would be 42 inches. Let's say we go to the wide end of the soil formation range and say it takes 500 years to create every inch of that 42-inch soil. What does that mean? 21,000 years. So I'd say for our soils, which have been sitting around and are very deep in the local area, and usually are somewhere in that 3 to 5 foot deep range, we probably have been weathering those soils in place for anywhere from 5 to 30,000 years. So they're pretty old and they've been here with us for a long time. And every time you see a little bit of soil eroding away after a heavy thunderstorm, you see that muddy flow of water going down the street or running off of your lawn. Think about the time that's being lost. Think about the amount of natural effort, how much weathering it took to create that little bit of soil that's now washing away and going down into our storm drains. Think about how long it might take to get it back. So soil is a renewable resource, but it's a very fragile one because it takes a very, very long time to recreate any depth of soil that gets lost.
Dan, we had some great questions come in about that last slide.
Sure.
The first is, does the soil require the organic element to be considered soil?
Does it require it? Not necessarily, but I don't think you would ever find a soil that doesn't have at least some organics in it. There's certainly some that have more than others, and obviously the soil in your vegetable garden, for instance, might have even more than what we would naturally find out in a forest or a field around here, because you could be adding a lot of your own organics to it, like compost and other amendments. But generally, specifically, no, you could theoretically have a soil that doesn't have organics in it. In practice, I think it would be very, 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 very rare to find that, though.
Thank you. And the second question is a two-parter. What constitutes broken down, and when is soil humus considered broken down?
Well, I don't have an exact definition for when it's broken down. It's more based upon what it looks like. So soil humus is just, it looks like black topsoil. So the compost pile is a good example. Your compost is considered finished when it looks like soil. If you're raking through your compost and you can still see banana peels and other obvious remnants of your lawn or kitchen clippings, then it's not quite fully broken down. When it looks like nice dark soil, then we would consider that to be fully broken down and soil humus. Now, when we add soil humus to we add that compost to our soil, when I was saying breaking down, it literally means that humus over 100 to 150 years will basically decompose into nothing. It'll become, be eaten away. So it'll totally disappear within about 100 to 150 years.
Perfect. Thank you. I'll let you know if we get any more questions.
Sounds good. Thanks, Ashley. Good questions. Now, what are the natural forces behind the formation of soil? What is causing that big chunk of bedrock or those unweathered organic materials to break down and become sand, silt, and clay and soil humus? Well, it's the 5 soil forming factors. These are the natural forces behind soil formation, and also the natural forces that cause a lot of variability in the soil. And they have an acronym, which is not a very good acronym, at least in terms of how it rolls off your tongue, but it's bad enough that I hope it's memorable. And if it's memorable, then it's doing the job it's supposed to do, which is to remind you what those 5 soil forming factors are. So the acronym is CLORPT, C-L-O-R-P-T. Now, don't get confused. There are 6 letters in CLORP, but there's only 5 soil forming factors, because the first 2, CL, stand for the first factor, which is climate. The next letter, O, stands for the second factor, organisms. R stands for relief. Relief is just another term for your landscape position, where you are in the landscape. P stands for parent material, and T stands for time. So climate, organisms, relief, parent material, and time are your 5 soil forming factors. What do they do? How do they affect soil formation? Well, generally speaking, of course, climate really has a strong effect on the rate and extent of weathering, how fast things weather or break down, and how thoroughly they do as well too. And the general rule is hotter and wetter climates usually cause things to break down and decompose faster, both organic matter and mineral rocks. So you get really fast breakdown in a place like the Amazon in Brazil, and you get really slow breakdown in a place like Antarctica, just because it's so much colder there. And you'll see this as we go, throughout even smaller areas like Virginia. The soils tend to get more highly weathered and often a little bit more acidic too, which is usually an indication of high weathering as you go from northern Virginia to southern Virginia and the climate starts to heat up. Organisms are responsible for both the addition and the breakdown of organic material. Where does a lot of organic material come from? Think of the leaf fall coming off the trees. Think of the dead grass blades. Think of the dying animals. But also from the death of animals within the soil food web as well too. They're all adding organic matter to the soil, but they're also, that soil food web, breaking down that organic matter. The bacteria and the fungi are great at taking formerly living organic matter and decomposing it, breaking it down, and turning it into soil humus. Relief, where you are in the landscape, really controls the amount of erosion and the type of drainage you find in your soil. And this one is probably the easiest one conceptually to understand. If you are on a very steep slope, for instance, you're likely to have more erosion there because as water from rainfall or snow melt hits that steep slope, a lot of it's going to rush off the surface. And the steeper the slope, the faster it'll flow. The faster you have water flowing over the surface, the more particles of sand, silt, and clay and organic matter it can pick up and erode. Drainage, the higher you are, generally the drier your soils are. If you're up at the top of the mountain, you're probably looking at pretty dry soils because water just flows in one direction, and that's downhill. And that's true whether it's flowing over the surface of the soil or flowing through the soil. Where are you going to find your wettest soil? Probably down at the bottom in the floodplain in the valleys. All the water is flowing there, and it's very common to have soils next to streams and rivers with high groundwater. You might have to dig down a foot or two, and you'll see free water standing in your soil in the hole that you just made. Parent material. We get a lot of traits from our parents. Soil gets a lot of traits from its parent material. So a lot of the chemistry, the acidity or basicity, a lot of the nutrient content we find in soil, especially some of the micronutrients like iron, zinc, manganese. The color of the soil, the texture of the soil, the sand, silt, and clay percentage, a lot of that goes back to what that soil formed from, the parent material that soil weathered from. To give you a local example, if we were to go out to western Fairfax County in the Centerville area, we've got a lot of two types of bedrock there, diabase, which is igneous rock, and shale, which is a sedimentary rock. The shale rock there tends to be very reddish in color because it contains a lot of iron oxide. And the soil that forms from it also tends to be very, very reddish because it contains that same iron oxide. If we go to the igneous rock, which can be right next to that shale rock, we tend to find that the soils that form there have a little bit higher pH and a little bit more calcium and magnesium and manganese. Why is that? Well, the diabase rock tends to have a lot of those chemicals within them. So as the rock weathers and forms soil, those chemicals go out into the soil as well too. Time is sort of a master variable. Remember, it takes 100 to 500 years to create every inch of soil. So these four previous factors, climate, organisms, relief, and parent material, need a lot of time to affect change, to start breaking down that solid rock or that unweathered organic material and turn it into the highly weathered, highly formed sand, silt, clay, humus that we see in our soils. Generally speaking, the older the soil is the deeper it usually is, and the more weathered it usually is. Younger soils often will be very thin just because they haven't had the time to sit there and weather away that bedrock down below them. And another thing that CLORP does is it gives you variability. As you go from spot to spot, the climate can change. The types of organisms that you'll see within the soil and above the soil can change. Your relief will change from over very small distances as you walk from the top of the hill to the bottom. Parent material can change as well too, and the time that the soil has been sitting there and weathering in place will change from spot to spot too. And as those 5 soil forming factors change, the soil will change as well too. So it's really the variability within CLORP that causes the variability within the soils that we see. In Fairfax County, we have about, I think, 109 different soil types. So that gives you an idea of how variable soil is from spot to spot. And this isn't geographic-wise a particularly large county. Population-wise, it's very large, but it's not very large in terms of its physical size. And some of those changes you'll see as CLORP varies from spot to spot are changes in soil colors, the depths of the soil, the chemical and nutrient content within the soil, the age of the soil, the depth to the water table or the groundwater, and whether that soil is acid or basic. A lot of those things are a result of the variability of the 5 soil forming factors. So kind of an overriding theme here with CLORP and the different types of soil it creates is that soil is not just plain brown dirt. You You can find lots of colors, lots of depths, lots of other variation from spot to spot to spot. So the soil you have in your yard may be very, very different than the soil that your friend has in his or her yard, even if they live just down the street. In terms of the scale range, when we're talking about changes in soils over very large scales, why is the soil in Alaska or northern Canada different than the soil here? Why is the soil here different than the soil in Argentina? It's really climate that we're talking about. Climate explains those big differences over big areas. At the more local scale, why is the soil in Western Loudoun different than the soil in Western Fairfax versus the soil in Alexandria? We're talking about the changes are really more due to changes in relief, the landscape position, and in the parent material. So this map shows you some of the main parent materials that we have. As we go out to the west, we're in the Blue Ridge in western Loudoun County. That's a mix of igneous and some metamorphic rocks. They call it the Blue Ridge, not because it's in the Blue Ridge Mountains now, but because the rocks that you find there were in the core of an old line of the Blue Ridge Mountains that weathered away many millions of years ago. And we get over to the Triassic Basin, which does fall throughout about a third, maybe about a quarter of Fairfax County, the western quarter. That is sedimentary rock, shale, siltstone, sandstones, and it's got its own unique assemblage of soils that weather from it. Then we get into the Piedmont, which I'm kind of sitting myself in Reston, right on the border of the Triassic Basin in the Piedmont. The Piedmont has a mix of metamorphic, igneous, and some sedimentary rock as well too. If you go to Great Falls or if you drive down the GW Parkway and you see those big gray blocky rocks sticking out in some of the cliffs and outcrops, you're looking at Piedmont bedrock. And finally, we get to the coastal plain, southeastern parts of Fairfax County, the city of Alexandria, most of County of Arlington. That soil formed from sediment that washed in from the old Potomac River, the ancient Potomac River, many thousands or millions of years ago. So you'd have to dig down, in some cases, 100, 200 feet to hit bedrock in the coastal plain. So the soil there just formed from waterborne sediment that washed in many thousands or millions of years ago. So those local scale changes make big changes in the types of soil that we find. And then within each of these parent material areas, there's also a lot of small changes. So if you're up at the top of the hill in your own neighborhood and you go to the bottom, you probably would find different soils if you dig in both spots. And that's not because the parent material changed. It's just because your relief changed, your landscape position changed. And remember, generally the higher you are, the drier you are. The lower you are, the wetter the soil is going to be. So this shows a very local change in soil type as we're going from the top of the hill to the bottom. So the parent material here probably won't be different at all. What is different is the relief. So as we go down further, we'll start to see one change. The topsoil generally gets thicker. When we get down to that wetland or floodplain down at the bottom, that soil stays saturated for a very long time. And saturated soils are full of water and very limited in their oxygen. Soils that have low oxygen tend to accumulate organic matter because it takes longer to break down that organic matter. The well-aerated soils up at the top of the hill that are nice and dry, that organic matter can break down fairly quick, so it never accumulates that thick, dark layer of organic material like the wetland soil does. And then you can also see, as we go down the hill, the soil in the middle goes from kind of a reddish, rusty red down to a grayer color, grayer. We'll talk about the importance of that gray color a little bit, but it's an indicator of wetness. So the grays show us that the groundwater is very high. So there's the 5 soil forming factors, and then there's something called the soil forming processes. And they're very interrelated. It's a little confusing. I'd say the factors are the more important thing to remember. But basically, as the factors work on the soil, these are the processes that they power, the general processes that their efforts create in the soil, which causes changes and movements of material within the soil. We've got inputs, translocations, transformations, and losses. These are just kind of fancy ways of saying things get added to the soil, subtracted from the soil, moved around within the soil, and transformed within the soil. So what are some of the inputs? And these aren't all of them, certainly, but some of them. There's organic matter. You think of that leaf fall during the autumn. Carbon. As that organic matter gets added to the soil, a lot of carbon is added along with it because the That leaf is made out of mostly organic carbon, but there's also carbon that's added through rainfall as carbon dioxide dissolves in that rain droplet as it passes through the atmosphere. The rain itself is adding water, of course, and oxygen diffuses down into the soil from the surface as well too. So those are all examples of inputs. As you get into the soil, things don't just lodge up at the top. They translocate, they move around within the soil. And one good example of this is clay. Generally, we have to dig down a little ways, 6 inches, 12 inches or so, before we start getting into the really clayey subsoil layers of our soil. But clay didn't form down there. It actually formed up very close to the surface. But over time, as water passes through that soil and washes through the soil pores, it takes those fine clay particles and washes them down deeper into the soil and deposits them in that subsoil. So over time, the clay content of the subsoil will increase, and the thickness of the clay layer in the subsoil will increase as that clay gets washed and driven down deeper and deeper and deeper over time. That's one way you can sometimes tell the age of a soil. If it has a really, really, really thick band of clay, it's probably been sitting there and weathering in place for a long time because it shows that the rainfall has deposited that clay over feet of soil over many thousands of years. Transformations, things change. As you go down to the bottom of the soil, you dig down deep enough, you will eventually hit fairly unweathered parent material. But as you go up in the soil, that parent material starts to decompose faster and faster until eventually it creates sand, silt, and clay. So kind of at the bottom of the soil, you're in that sort of transition zone. It's parent material that's kind of halfway between the original parent material, maybe bedrock, but not quite fully weathered into those sand, silt, and clays that we see up at the top of the soil. It's maybe a gravelly mix of partially beaten down, partially broken up bedrock. And then lastly, there's losses. Things will wash out of the soil as well too. And especially things that are soluble, things that are easily dissolved, like some of the nutrients, which are very important both for soil quality and soil fertility, but also very important because they can be a pollutant if they wash down into our groundwater and into our surface waters. But you will find even in natural systems, there's quite a bit of leaching of those soluble nutrients. Like nitrate is a good example. That's a very soluble one. They leach out of the soil column and down into the groundwater, or flow sideways and leach out into our streams and our rivers. What does soil look like? If we were to dig in our backyard or in the nearest park, we would find that soil kind of looks like a layer cake. It's got different layers. We call these layers horizons. So it's going to look very different as you go from the very top to the very bottom. These are the names of all the potential horizons you can find in soil. It doesn't mean you're going to find each of these horizons in your soil. These are just the maximum number that you could find. There's the O horizon, the A horizon, the E horizon, the B horizon, the C horizon, and the R horizon. And that's in order from top to bottom, O, A, E, B, C, R. Let's talk about them. So your O horizon, think of O as standing for organics. It's your surface layer. It's the surface litter, the loose organic litter of partially decomposed material on the surface. So easiest way to see the O horizon is to go to the forest. You see that, what we call the forest duff, basically that layer of decomposing leaves, twigs, and other stuff right on the soil floor, right on the forest floor. That's your O horizon. So that organic matter that's just beginning to break down, but in many cases you can still tell what it originally was. That was a leaf, that was a twig. Then we get into the A horizon, and this often is where people really think soil is starting. It's our first subsurface layer, so we do have to dig down below the surface to get it, unlike the O horizon, which is sitting right there on the surface. And this, colloquially, this is what people refer to as topsoil. When they're saying topsoil, they're really meaning the A horizon and vice versa. When we say A horizon, we also mean topsoil. So when you go buy a bag of topsoil from a Home Depot or wherever, you're basically buying bagged up A horizon. It almost is always this dark brown or black color because it's very rich in organic, specifically soil humus, that decomposed organic material, decomposed resistant organic material. Soil humus is usually black or dark brown, so the more you see of it in the A horizon, the darker that A horizon is going to be. This is also our biological powerhouse of the soil. This is where you'll find the most concentration of bacteria, fungi, and plant roots, as well as all the other organisms involved in the soil food web, because the soil food web is driven by organic matter. So where you have the organics breaking down and being added to the soil as soil humus, that's where you're going to find all of your other critters in the highest concentrations. Now in Virginia, I'd say our average topsoil is only about 2 or 3 inches deep. So if you're looking for the A horizon, it's going to be right there up at the surface, and it's usually not very thick. And generally you can tell where it is and where it ends by the change in color. Below this, we may, not always, but we may get an E horizon just below our A horizon. I think of E as standing for exit. It's sort of a naturally weathered, naturally leached layer. Leach means just a washing of material out. As the A horizon forms, it creates a lot of natural acids as organic matter breaks down. As rainfall is added to the soil, it brings in dissolved carbon dioxide, which creates its own acids as well too. So the E horizon is sort of what evolves over many hundreds of years as those natural acids kind of work their way through the soil and leach and weather materials out. So the E horizon probably had a nice dark color or orangey yellow red color like we consider a lot of our soils to be at one point. But natural acid weathering has sort of washed all those colors away, and what's left behind is kind of a pale, almost washed out grayish kind of horizon. So the analogy I use, if you get a new t-shirt that has a really bright color and then you throw it in the washer at the highest possible temperature, what happens? A lot of the color bleeds out. That's kind of what happened to the E horizon. A lot of the color and other material within it bled out, leached out over time. And again, like the A horizon, the E horizon, if it even exists, and I'd say it exists in less than half of our soils around here, it's going to be pretty thin. 2 or 3 inches thick is about as thick as you'll see E horizons around here. Where we do find thick horizons is down at the B horizon. This is where you start seeing what we usually call, what people locally call red Virginia clay. You're starting to see some noticeable red, yellow, or orange colors. You're probably getting down into the B horizon, but the real test of whether you're in the B horizon or not is what is going on with the clay. If the soil is feeling stickier, denser, just generally feels like there's more clay in it, chances are, again, you're in the B horizon, because the B horizon is where the clay deposits. As it washes down through the soil, it deposits in that B horizon. So if you see that sticky, dense feeling soil, and especially if it's sticky, dense, and also has that yellow, red, or orange color, very good chance you're in the B horizon. And the B horizons, we can get very thick layers in Virginia. It's not unusual to find a B horizon that's 18 or 24 inches thick. So unlike the A or E, this can be a fairly large, thick horizon. Then we get into the C horizon, which is sort of our transition zone. It's the border between the highly weathered A, E, and B horizons above and the unweathered parent material down below. Usually in our case, that parent material is bedrock, but if you were out in the coastal plain, it would be unweathered sediment. So if you are on top of bedrock, like most of us are, as you're digging down into the C horizon, what you'll likely find is that the clay content of the soil starts to decrease. You might also see an increase in more coarse materials like sand and gravel as well too. So if the soil feels like it's getting drier, it's getting looser, it's not sticking to itself, it's not holding as much water because you're losing that clay content, and it's also getting those big grits of sand and gravel. It's a very good chance you're down in the C horizon. And then below that, we have our R horizon. It can be tough to tell where the B ends and the C starts because that can often be a very gradual transition, and you don't always get a real clear color change either. So look for those changes in the feel of the soil, the texture of the soil. Is the clay content dropping? That's how you can usually tell you're in the C. The R horizon, how do you tell? You're hitting rock. You can't dig down any further. If the stuff under your feet feels really solid and you can't dig with your shovel any longer, chances are you're in the R horizon. So another important aspect of how soil looks, it's not the layering, but something we call the soil structure, which refers to how the soil solids are arranged together. We talked about soil texture before. One of the other really important physical characteristics of soil is the structure. We find that soils tend to clump together into little aggregates that we call PEDs. And this is very important because this is how the soil is allowed to have that pie chart that we saw at the beginning, 50% solid material, 25% air, 25% water. As the soil clumps into PEDs, inside the PEDs you'll find little micropores, and between the PEDs you'll find macropores. Those macro and micropores can be filled with air or water, And that's what allows half the soil to be open space that's filled with that, again, that 25% by volume air, 25% by volume water. A soil that doesn't have this good structure can't hold that volume of air or water. And you need those big pores as well, those macropores, to allow air and water from the surface to even get into the soil in the first place. So you really do need good structure because it tends to create a soil that's loose feeling, light, easy to dig, but really the important part of good structure is that you've got these nice beds that hold together pretty well, but you've got these big pore spaces in between that allow passageways for air and water to get down into the soil. Ideally, what you want to see are these two types of soil structural PED units. The little ones down at the bottom are called granules. That's granular structure. They look kind of like grape nut cereal. This is called blocky structure. You often find granular structure in a nice healthy A horizon topsoil and blocky structure in a nice healthy B horizon subsoil. And they pretty much look the same except for their size. The shape is pretty much the same. And the reason it gets bigger down in the B horizon is because the clay is there causing everything to stick together. Fortunately, what we find a lot of in urban areas is this platy structure, which is often a sign of compaction. If you take this nice, loose, well-structured, granular or blocky soil and you run it over with some heavy construction equipment, chances are you'll get that platy structure. Sort of a sign that the soil has been packed down and squished and compacted. So here's soil structure in sort of real life. There's granular, there's blocky, there's platy. And again, platy is often an indication of compaction. And when a soil is platy, it usually means a lot of the pore spaces have been squeezed out. So now that soil is probably more like 60, 70, maybe even 80% solid material and only 20 to 30% air and water because the pore spaces have been squeezed out. So good soil structure means firmly developed beds that are adhered well to each other, but also have these big pore spaces in between to allow air and water to get down into the soil. Soil colors are important too because they can tell you stuff about the soil. For instance, organic matter. The darker your soil is, generally, the higher the organic matter. This is probably from a peat bog right here. We're not going to find a soil like this anywhere around here in Virginia, but those really dark black colors are a very good indicator that there's a ton of soil humus in here. And this, on the other hand, is a soil that's very, very red. When you see a soil that's dominated by reds, yellows, and browns like this, usually means a pretty dry soil. A soil that does not have any groundwater or saturation within at least the depth that we're looking at. If, on the other hand, you pull out the soil and you see these splotchy gray colors, especially splotchy grays that are kind of mixed in with other splotchy reds, yellows, and oranges, we call that a mottled soil. And the gray color is a great indicator of saturation. The gray is telling us that that soil is saturated for a good couple, at least a minimum of a couple weeks every year. More likely in this case, probably several months, seeing how big those gray colors are. Gray colors will occur in your soil when it's wet for at least 2 or 3 weeks in a row, oftentimes much longer. But when the soil is totally saturated, meaning every single pore space is full of water and there's no oxygen in it, the ions that create the rusty red iron oxide colors will dissolve and wash away. And when they wash away, you start seeing those gray colors. It's almost like the dye of the soil, the red, yellow, orange dye of iron oxide washes and dissolves away, and you're left with just these gray splotches that are sort of lacking any other color. So those grays are really good indicators of the water table. And remember, though, these are all general rules. It's always very important to look around you. The landscape position that you're in can tell you a lot about the soil. You're finding some grays like this, but you're at the very, 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 very pinnacle of a hilltop or a mountain. Maybe it's caused by something else. Maybe the soil just has some naturally gray parent material. But if you're down in a stream valley, in a floodplain, and you see those grays, that's a much better indicator that what you're indeed looking at is the groundwater table, the wetness saturation. So sort of use your common sense and look at the landscape when you're trying to interpret what the soil is trying to tell you. And then there's a special type of soil, and it can often be identified by its gray colors, called hydric soil. And hydric soils are the soils that you will find in wetlands. And in fact, in order to be considered a wetland by legal purposes, meaning a wetland that is protected by natural resource laws, a wetland that cannot be developed, or if it is developed, you have to make up for it somehow. That wetland has to contain hydric soils to be legally considered a wetland. And hydric soils are basically poorly drained soils that are mostly gray, where you see these gray throughout a majority of the surface areas of those soils. If it doesn't have that hydric soil, we actually don't consider it to be, legally anyway, a wetland. So again, we're looking at that same, were there some questions? Oh.
Yes, we just had the one.
Sure.
We wanted to know, how do you fix Blocky Structure? Do you dig it up to aerate it?
Aeration can help. It can be a slow process, but basically if you do aeration in your lawn, that can be helpful because it gets oxygen down into the soil. But generally speaking, the way to fix Blocky Structure, assuming that it's not so severely compacted that nothing will grow in it, the way to fix Blocky Structure is to get a lot of things to grow in it, because as you get the roots working its way down through the soil, the roots themselves, as they grow, they create pore spaces. They're pushing through the soil, they're tunneling through the soil. And as the plant grows, those roots will exude organic matter, spit organic matter out into the soil. And that organic matter is actually very low density. Organics are a lot less dense than the mineral material. So as you start pumping that low density organic matter into the soil, it loosens the soil, it lightens the soil, but organic material, as it decomposes and becomes humus and sort of the decomposition process creates sort of a natural glue-like substance, which actually helps the soil stick together and create those new soil beds. It's sort of the glue that can hold the soil beds together. So the short answer is get a lot of stuff to grow on it, get organic matter into the soil as a result of all that growth, and power up the natural soil food web. And that will, over time, allow your soil to get a good structure and to lessen its density.
Perfect. Thanks, Dan.
Thanks. All right, so looking again at that same picture we showed of the soil type, that doesn't really change so much except for its landscape position as we go from the top of the hill down to the bottom of the hill over a very short distance. We already saw that the A horizon changed its thickness. We got a thicker A horizon as we got into a wetter and wetter soil because organic material breaks down at a much slower pace in a saturated soil. The other change we saw is the subsoil color. So as we go down, you'll notice that the subsoil, as we go from the top to the bottom, starts getting more and more pale. It starts off as pretty kind of a brownish, reddish, kind of a rusty reddish color. And as we get down lower and lower, you see more and more of those gray materials being added to it. And that's not necessarily because the parent material is changing. It's just that the soil is wetter for a longer period as we get in the landscape. And as it gets wetter, it stays saturated for longer, and this allows a lot of those iron oxides, which color the soil that red, yellow, or orange color, to wash away. And instead we get those gray splotches, which again are indicators of wetness. So that's kind of a whirlwind overview of what soil is and some of its variability and how it forms. But why is it important? What roles does it play? Why is it an important natural resource? Well, there's physical support, which I won't get into so much, but we need something to hold up our trees so they don't fall down. But what we're really going to talk about is the water cycle, the nutrient cycle, and carbon sequestration. So you can think of soil as being sort of a global sponge and a global filter. When water falls on the soil surface, it can do a couple different things. It can soak into the soil, it can run off the surface, or it can evaporate or transpirate back into the atmosphere. And ideally, we want as much as possible of that water to soak in the surface, soak down into the surface of the soil, and as little as possible have runoff over the surface for a couple important reasons. Well, again, soil is like a big filter. So as you're dropping water onto the surface, anything that's on the surface of the ground could potentially be dissolved or just washed away by that water. Maybe that's nitrates, which is something we'll find in manures and especially in fertilizers. Phosphates, that's a part of fertilizer as well too. Bad bacteria, bacteria that could cause illness or sickness, both in animals and plants and humans. Oils from the roadway, pesticides, other pathogens, viruses, things like that. Luckily, as the water passes through the soil, It passes through clay and humus and soil microbes, and a lot of this stuff actually sticks to the surface of especially clay and humus, and then the microbes themselves have an opportunity to come and sort of attack them and break them down. The microbes don't break down nitrates and phosphates. They actually use nitrates and phosphates, just like we need nitrate and phosphate, nitrogen, phosphorus being very important nutrients. The microbes can use it too. So they take it up and add it to their own body to power their own growth. But they are also, remember, there's billions and billions of these microbes living in the soil. If there's any bad bacteria or other pathogens, chances are these good microbes in the soil will kill them off and just totally eliminate them. In addition, there's, the oils and the pesticides and other potential pollutants. Well, as long as it's organic, and by organic, I simply mean it contains organic carbon. As long as that pollutant is organic and not added to the soil in such a high concentration that it kills off all the native microbes, those microbes will eventually be able to break it down, whether it's an oil or a pesticide, gasoline, something like that. They can break it down. It just needs to be not so concentrated as to be toxic to everything. So over time, as the microbes break down the oil and pesticides and turn them into harmless byproducts, as they use up the phosphates and nitrates and other nutrients, and as they kill off the bad bacteria and viruses and other pathogens, what they in effect do is they clean the water. So it sounds strange, but if you pass water through dirt, it actually comes out a lot cleaner. In addition, a lot of the water stays in the soil. The water itself is attracted to the surfaces of clay and humus, which is great because if all the water just passed through the soil very quickly, the plant roots wouldn't have any access to it. And the plant roots only take up two things from the soil. They take up oxygen and they take up water. So it's very important that the water stays in the soil for the plant roots to have access to it. Otherwise, they'd just be wilting and dying. But we're disturbing the water cycle, especially in urban areas, but also in agricultural areas too, through imperviousness. So imperviousness means impervious surface is any surface that doesn't let water pass through. Hard top, black top, asphalt, rooftop, all these things. If you put an impervious surface down, the water can't get into the soil in the first place, and rather it's going to become surface runoff. But if you compact the soil, same thing happens. Compacted soil isn't totally impervious, but it can take in a lot less water than that loose natural soil that you find in well-managed gardens and forests and farm fields. And what happens as a result is that as imperviousness and compaction increase, we get a lot less filtering of the water through the soil, so the water remains polluted. We get more stormwater runoff, a large sort of first flush, if you will, of stormwater. This stormwater flows down into streams, and it causes erosion within the streams. The streams are kind of having a little mini flash flood every time it rains, and they start to erode wider and deeper to accommodate this huge flow of stormwater that normally would have soaked down into the soil, but isn't allowed to anymore because of the imperviousness and compaction. And as those streams erode, the sediment from the stream bank further pollutes the water. So we've got polluted runoff that's getting further polluted by the erosion that it's causing and the sediment that gets deposited as a result of that erosion. So it's a double whammy, if you will. Next, moving on to the nutrient and carbon cycle. So, I mentioned them as separate cycles, but really the nutrient and carbon cycle are the same cycle, if you will. We can kind of break them down and describe them separately, but it's really the same cycle. As nutrients are floating around, a huge pool of carbon is cycling around with it as well, too. And remember, the soil food web is sort of the way that nutrients and carbon cycles its way through the soil. It starts down there at the bottom as organic matter. The materials that get exuded or pushed out through roots, as well as all the dead organic material that deposits on the soil surface and it gets incorporated into the soil, as well as the death of any of these critters that play a part in the soil food web. If they die or they defecate, that material gets added to the organic matter as well, too. And that organic matter is first processed by our microbes, our fungi and our bacteria, microscopic microbes. So really, these are the basis of the soil food web. The organic matter is the original energy source, but it's the fungi and the bacteria that sort of kick them off and start the decomposition and processing of them. And as they decompose and process the organic matter, they also release nutrients, but they also, of course, incorporate a lot of that organic carbon that they're eating into their own body so they can create new bacteria and new fungi. And then there's a whole multiple layers of other predators and feeders that eat the fungi and the bacteria and thus are bringing in the nutrients and the carbon into their own bodies as well too. Now this is important not just in the soil, but globally. Because again, we've got our decomposers, and that's just a general term we can apply to the bacteria and fungi within the soil. Any organic carbon that gets added to the soil, whether it's a dead animal, a manure, leaves, what have you, has got a ton of really good nutrients tied up within the structure of that organic material. But that nutrient can't be released, unlocked, and used until the decomposers get at it. The decomposers break down, and as the name implies, they decompose that organic matter. Luckily for us, as they do that decomposition, they're sort of sloppy eaters. They leave crumbs around, crumbs full of nitrogen, phosphorus, and potassium. So the decomposers need to get out of that organic matter in order to break it down and release the nutrients in usable forms. And luckily for us, they do that. And as they decompose this organic material, of course, they're taking in nutrients for themselves, but they're also leaving these crumbs of nutrients out in the soil, some of which can dissolve in water. And those soluble nutrients are the ones that are available to the plants, the producers. Remember, roots only take up oxygen and water through soil. So how do they get their nutrients? Well, the decomposers have to work on that organic matter and process those nutrients so that they can become soluble and dissolved in water, so that when the trees and other plants take up water through their roots, they're also taking up those dissolved nutrients. So the decomposers make it possible. They put it in the right form, the right format for the nutrients to be dissolved in the water to go up into the plants. And then once they are up in the plants, those nutrients power new growth, and that becomes the base for our soil, or excuse me, our food web. Think of all the plant-based materials that you eat. And even if you're a carnivore, you're eating a hamburger, what did that cow eat? The cow was eating grass and other stuff that was growing from the soil and thus taking in nutrients from the soil. So all of our nutrients eventually go back to the soil. Now, your average soil microbe, your average soil bacteria, likes a food source that has about 24 parts carbon to 1 part nitrogen. So if you imagine with our nutrient cycle, there's an atom of nitrogen circling around that cycle, going into the soil, being processed, going back up into the above ground soil, the above ground food web, and then return back to the soil. There's a pool of carbon 24 times larger that's circling around with it. So the nutrient and carbon cycles really are the same thing. And from a purely carbon point of view, we find that soil is a carbon sink, which means it takes in more organic carbon and stores it than is released from it as carbon dioxide. As the microbes break down that organic matter, about half of the organic material does become carbon dioxide and return to the atmosphere. But the other half stays in the soil for a long time as soil humus and gets stored there. And that's how soil can become a carbon sink, by building up this soil humus and undecomposed carbon over many hundreds or thousands of years. We find the highest concentrations of soil carbon storage in our northern latitudes. Unfortunately, this is also the area where we're seeing warming occur the fastest. And as that soil warms, some of that organic carbon that's been stored there will start to break down. As the soil warms, you get more microbial growth, and the more microbes you have, the more quickly they can break down that stored soil carbon. So there's problems, there's benefits, and there's problems. We've got all the stored soil carbon, but some of it, in fact, a lot of it, could become carbon dioxide if we keep warming the planet and warming our soils. But we can also see that through changes in modern farming, we can either increase or decrease the carbon storage within our soil. So if we do the right practices and increase our carbon storage, our farm fields, even on a smaller scale, our gardens and our lawns can become better carbon sinks and actually suck carbon dioxide out of the atmosphere and store it underground for hundreds or thousands of years. So potentially soil is a big combatant in the fight against global climate change. But we are doing a lot of things wrong right now as well too. So one way we disturb the nutrient and carbon cycle is we till and we overgraze. When we till soil or plow the soil, we basically are flipping it up and exposing the soil and all the organic humus that was stored in there to the surface. And when you've got bare soil like this after it's been freshly plowed, you can get a lot of erosion. If we have a big storm, thunderstorm that falls on this farm field, we're going to lose a lot of our topsoil through erosion. We also lose a lot of microbes. Just the think of those plows. They're basically like knives that work their way through the soil, cut through the soil. This tends to kill off a lot of those soil microbes, but especially the soil fungi. Because remember, those soil fungi are microscopic, but they exist as those long, long root hairs. And these plow knives will come through and cut those root hairs and kill the fungi. We also get a loss of organic material, stored soil carbon and soil humus, because when you flip the soil up and you expose all that nice dark topsoil to the surface, you're exposing it to a much more concentrated hit of oxygen. This tends to oxidize the organic material and break it down into carbon dioxide at a much faster rate than it would have if it had been protected underneath the surface in the A horizon. We also find that in agricultural soils, we have a suppression of microbes because we add a lot of fertilizer. Now, plants are kind of lazy. They're sort of like us, you know. Is it easier to make your own dinner, or is it easier to go to McDonald's and get something to the drive-through? It's a lot easier to have somebody else do it for you. So the plants are kind of the same way. If the farmer is putting down a lot of fertilizers, that's supplying the nitrogen, phosphorus, and potassium that the plants need. They don't need those microbes as much. They usually shoot out organic material through their roots in order to feed the microbes, because the microbes then power the soil food web, which allows nutrients to be released and given to the plants. But if the plants are getting the nutrients they need from the microbes, they don't send out nearly as much organic carbon into the subsoil, and it tends to suppress the soil food web, especially the base of the soil food web, those microbes of bacteria and fungi. And then another problem is, with over-fertilization, we can affect water quality. We put too much fertilizer on our fields, and a lot of it washes off. It washes down into our streams and our rivers, Chesapeake Bay, and that causes eutrophication, which is basically an overgrowth of plants in the water, things like algae, lily pads. And this can block out sunshine and soak up available dissolved oxygen as well, too. So water quality is in many ways related to soil quality. So we have sort of a new paradigm for soil health and managing your soil. We want to rely less on the old forms of agricultural and also, soil gardening care, which is fertilization and tillage or plowing. And instead, we want to feed the soil microbes. If we feed the soil microbes, we are in effect feeding the soil food web, because what do the soil microbes eat? They eat organic matter. So you get more organic matter into your soil, feed those soil microbes, you'll have a healthier, more self-regenerating soil food web. And this leads to a healthy self-generating nutrient cycle as well, too. And if you can get this up and running, you don't have to manage your soil nearly as much. If it's already got that healthy food web and that healthy nutrient cycle that goes along with it, there's not all that much more that you need to do. So again, this is from the U.S. Department of Agriculture. They're pushing 4 new principles for managing soil health. And they do it for farms, but there's no reason it can't be applied to the suburban landscape as well, too. They say maximize biodiversity. Basically, you want to grow a lot of different things. This isn't your monocrop of corn or soybeans. This is a cover crop with 7 or 8 different species, because what we find is the more diversity you have above ground, the more diversity you have below ground. Different microbes tend to favor different types of plants. So the more species of plant you have growing on your soil, usually the more diverse your collection of microbes is below the soil. And generally speaking, with all ecosystems, the more diversity you have, the stronger and more balance you have. Here's another good example of smaller scale. So here's a big garden, but still a garden showing lots of different types of plants growing, as well as some flowers on the edge to attract pollinators. You want to maximize continuous living roots. One of the best things you can do for your soil is to keep something growing on it as long as possible. You don't want to have your soil sit fallow like this farm field, just have it sit bare. Rather, you want to have a cover crop, something growing over the winter, just something growing on the soil for as long as you possibly can. Because when those roots, living roots, are growing on the soil, down in the soil, they are putting out organic matter into the soil and feeding the soil food web. And you want to maximize soil cover and minimize disturbance, which really kind of go hand in hand. They're sort of the same thing. Sometimes you do have to plow. If you do, try and take as light a touch as possible. The picture up here is showing what we call no-till farming. Basically, the farmer is growing a winter cover crop, which doesn't get harvested. It's just there to hold the soil in place and have living roots on the soil. and then they're rolling over that cover crop with what's called the crimper, which basically pushes down the cover crop and cuts it up to kill it, but it leaves all the residue of that crop right on the surface. So the soil is always covered, even though the cover crop is now dead, and they can come in with their conservation till, which cuts just a little tiny furrow into the soil, drops the seeds down and covers it back up. So they're not exposing all of the soil, they're just exposing this little slit of soil where they can drop the seeds in and cover it back up immediately. So that's both maximizing cover and minimizing disturbance or tillage. It doesn't have to be complicated. Covering your soil can be as simple as, putting a little mulch of straw or even leaves that you collect from the backyard on top of the rows of your garden or something like that. And sort of getting towards the end, I know I'm running a little long. If you're interested in soil, you want to know what kind of soil you have. To really manage your soil, you have to know what soil you have in the first place. And the best source for figuring out what the soil is that's mapped on your property or your farm field or your friend's property is the soil survey. Soil survey is basically a collection of maps and data tables that describe the soil types within an area, usually within a county. And you can go to the web soil survey. I didn't include the URL here because it's really long, but there's only one web soil survey, so any search engine you use, just type it in and it'll take you there. It's run by the U.S. Department of Agriculture, and you can find soil maps for almost anywhere in the United States. And connected to those soil maps are, again, data tables that show the physical and chemical properties of the soil, like the horizons, the color, the drainage, the expected nutrient content, and pH, and amount of organic matter. And importantly, too, it also describes the suitabilities of that soil, what it's good for, what it's not good for. Could you grow corn, soybeans, or the other cash crops on it? Could you have a garden? Or is it more suited for wildlife habitat and aesthetics because it's just not fertile enough for that commercial crop production? The soil survey will tell you. It's general, of course. Soil changes from spot to spot, so we can only give general ratings, but it is very useful. And it's got a whole bunch of ratings in there. And chances are, as you go through your tests, you will see a couple. You'll probably be given a sample of material from the soil survey and then asked to find or reference the soil survey to find whether this soil in this field is suitable for X, Y, or Z crop and what your expected yields are. And if you were going to build a house in this field, would you be able to put in a basement because the water table is low enough that it would allow it, or is it too high and the basement's going to flood? Things like that. And that's it from me. I'm leaving my contact information there because I welcome any questions. So, of course, ask questions now, but you are also very free to send me an email or give me a call if a question should arise as you're preparing later on. So, Ashley, do we have any other questions?
We do. We had a question pop up. Why not plant a cover crop that can be harvested?
Well, you can, and some people do, but sort of the idea of the cover crop is you're putting it there to hold the soil in place and also to add organic matter to the soil. So the picture I showed of the farmer kind of rolling down that cover crop, what in effect they are doing is killing it in place. So it's going to decompose right on the soil and add a ton of organic matter to the soil as it decomposes over the next couple months. So it sounds a little odd because it does cost money, but the idea is you actually save money by adding organic material, organic carbon, and the nutrients that were contained in that cover crop, recycling it back into the soil. So you probably have to pay for less fertilizer, less pesticide down the road. So, and studies have shown that with cover crops, you can save money in the long run by increasing your soil fertility, which will increase your yields and less need for management on your part. But having said that, there are some cover crops that you can harvest. But by harvesting them, you are removing that organic matter from your farm field, from your soil. So in some ways, it does take away from the benefit of the cover crop. But of course, you can sell it and get money for it too. So there's a benefit there.
Thank you. I'll see if we have any other questions come in. And if anybody else has one, feel free to enter it in the chat box. I was wondering, since our special topic this year is water resources management, how does the health of our soil relate to the health of our drinking water and the quality of that?
It's a very close relationship. And generally what you'll find is, well, we'll start with the urban area because that's where we live. the more development, houses, shopping centers, office buildings, schools, roads, that you have within your watershed, within that area of land that drains down to your drinking water source, whether that's the Occoquan Reservoir or the Potomac River, generally the more polluted that water is going to be. Because when you have all of that development, you both have the pollutants that come with it. You know, roadways will have oil and other drippings from cars, and farm fields will have fertilizer and animal manures, and suburban houses will have fertilizers and pesticides on the lawn. That stuff can get washed off into our streams, but perhaps just as importantly, in the urban environment, we have all that compacted soil and those impervious surfaces, so that polluted water never gets the chance to soak into the soil and get filtered. And instead, it's flowing into our storm drains and then off into the nearest stream. So it's sort of putting that pollution directly into what eventually will flow into our drinking water source. Whereas if you have more natural environment without those impervious surfaces or compacted soils, that water does have the opportunity to soak down into the soil to a much greater extent. So if there is any pollutant within that water, the vast majority of it will get filtered out in the soil itself. And by the time it flows down into the groundwater or flows off through the shallow groundwater and leaks into the banks of our streams and our rivers, it's been cleaned. So you really do want to pass that water down through the soil first before it gets to your drinking water source in order to get that necessary filtering.